So now that you've heard about the specific notification pattern, we're going to go ahead and cover the skeleton and specification and so on for assignment number 4. So the purpose of this assignment, the objectives, are basically to learn how to synchronize the beings, which will be implemented with async tasks, just like you did for assignment 3. Except now we're going to use a concurrent hash map and a FareSemaphore that's implemented using the specific notification pattern. I will describe concurrent hash map probably Wednesday. You can take a look at somebody else's description here. I looked around and found I didn't have any videos of myself describing it, but this one is enough to get you started. We're only going to use a handful of methods on concurrent hash map, as you'll see when we talk about the skeletons. And the specific notification pattern. This is my older video that I just described that was a little longer than the one that we just did, but they both have roughly the same information. So watch those videos, and of course, we'll cover the topics in class. So what you're going to do is you're going to take the solution that you did for assignment 3, in particular the async task stuff that was the focus of assignment 3A. But obviously, please start with your solution that you're going to use for assignment 3 altogether, right? Because I want you to have the best features that address all my comments and so on. So use whatever version is your final version of assignment 3 after you address my comments. Use that for the being manager, and then you'll go ahead and implement a new Palantir manager. And the focus here will be on this thing called Concurrent Map FareSemaphore, which we'll talk about in a second. And there's some tests, both JUnit tests and instrumentation tests. We may come up with some new unit tests. We'll see. They'll probably get done before the final submission has to be turned in, so you may have to update things to get an updated version of the test. The current test should test the properties of fairness, but we might get a chance to do some cooler Mockito tests that will look inside your implementation and suggest bugs that you may be having that are more subtle. Okay, so here's the stuff that you actually have to do. In the Concurrent Map FareSemaphore folder, you will see that there's a Concurrent Map FareSemaphore manager, and you'll have to implement essentially the acquire and release methods there. And you'll be using a concurrent hash map and the FareSemaphore that we'll talk about in a second. I'll also talk more about the concurrent hash map when we look at the skeletons. There's also 2 other files there that you have to modify. There's another file we'll talk about that's just an interface for both these things. Undergraduates are going to use a monitor object implementation to implement a FareSemaphore using the specific notification pattern with built-in monitor objects. And grad students get to do the same sort of thing, except using reentrant locks and condition objects. And they're slightly different. It's kind of interesting to compare and contrast the 2 solutions. The undergrad version is a little bit more compact because the code for monitor objects is kind of built in syntactically into the language. The grad student version with the reentrant locks and condition objects is a bit more verbose, just because you've got to do locking and unlocking and waiting and so on using the reentrant lock and condition object interfaces, which are ever so much more verbose. But you'll see that there's a couple cool little tricks you can play to make it a little more optimized. As always, it's correct if you run your test programs and everything works. And don't be surprised, however, when you first run this thing, if you get deadlocked, because that's most likely the problem that you'll run into, especially the monitor object version. You can grab all your skeleton code from GitHub here at this link, and you can just go ahead and fill in to-do marks. Keep in mind, again, this is really just focusing on the Palantir manager side of the house. We're just going to reuse your async task stuff. Okay, and the point of this is to get you familiar with synchronization using concurrent hash map and the specific notification pattern implemented using the appropriate synchronizers we've been talking about. Okay, so that's an overview of the specification. Now that we've talked about the specification, let's go ahead and take a look at the skeletons. As you can see, the place to focus on is Concurrent Map FareSemaphore. That's the folder within the skeletons that I have uploaded to GitHub. And as you'll see, there's a couple of things you've got to look at. I'll start by just giving you the simple interface. This is the FareSemaphore interface. So here you can see FareSemaphore is an interface, and it's just got 4 simple methods. acquire uninterruptibly, which won't be interruptible, acquire, which can be interrupted, release, and available permits. Those are the 4 things that you'll have to implement. And then, as I said, there's a couple different ways to do this. So I think what we'll do is, first we'll take a look at the manager that's kind of driving all this stuff. Then we'll take a look at the skeletons for the FareSemaphore. That's where all the complexity lurks in this assignment. So you can see here, we have a concurrent map FareSemaphore manager. It's going to have a field called available Palantiri, which is a FareSemaphore. Undergrads will implement one variant, grads will implement another. We'll see how that works in a second. And then we've also got our concurrent map, which has an interesting comment. You can ignore that. For the most part, it's already solved for you, but it's a weird bit of inconsistency between different versions of Java. The concurrent map will be implemented using a concurrent hash map. There are different kinds of concurrent maps, but you're going to be using a concurrent hash map. And it's going to be a concurrent hash map that maps Palantir to Boolean, where the Boolean are used to keep track of whether the Palantir is in use or not. That part should be very familiar to you. We've done that a gazillion times before. Here is the build model. Factory method, this is the thing that does the initialization of the internal state of those fields. And you'll have to create a new concurrent hash map. That's pretty easy. Iterate through the list of Palantiri using the same techniques you had before. Initialize each key in the hash map with true to indicate it's available. You've done that before as well. And then also initialize the semaphore, which is the 3rd field we talked about, using a fair implementation. And in this case, the grad students must say, new FareSemaphore CO for condition object, and the undergrads have to use FareSemaphore MO. But otherwise, it'll look the same. You're just changing the kind of semaphore. And as usual, we make this easy by factoring out commonality by using the FareSemaphore interface, and we just make a different implementation. OK, so far, so good. Here's the acquire method. Now, acquire is actually, it's very subtle. It's really simple in terms of code. There's not much code at all. But you have to think carefully about sort of why the code does what it does and how you write it. And I'll explain it here momentarily, and then you'll have to think about it some more. So the key thing to remember is unlike every other example that we've done with the Palantiri manager, we'll have no explicit synchronizers in acquire or release at all. So if you think back to the things that you've written, we've used spin locks, we've used reentrant locks, we've used, I think we may have used synchronized statements maybe, we've used stamp lock, that's what we're doing now. All those things you had to explicitly acquire and release something one way or another, right? Lock, unlock, acquire, write lock, try to upgrade, all that kind of stuff. In this case, we're not going to have any synchronized statements or any synchronizers in this method at all. And when I say there should be no synchronized statements, I don't mean, define a reentrant lock and use lock. I mean there should be no synchronizers, explicit synchronizers in this code. This will all be handled by the magic of concurrent hash map. And as we'll talk about later, concurrent hash map has this really cool method, and I give you a hint when I say atomically replace, hint, hint. There's a method called replace. And replace works very much like compare and swap, if you remember compare and swap that we talked about when we discussed spin locks. And the idea with replace is you say, replace this key, which will be a Palantir, obviously, to this value if the current value is that. So that's what you're going to have to do. You're going to have to use the replace method, and you're going to have to do this. You're going to have to try to do this atomic replace. If it turns out that the value is not what you would like it to be, then replace fails. If it turns out that the value is what you want it to be, replace succeeds. And when it succeeds, it does the atomic swap, or atomic set, really, atomic replace. So it's really, really simple code. We've got to think about how it's going to work, and you have to think more deeply about what does it mean to do this. Now, the thing that's kind of funky and tricky about this is concurrent hash maps, the operations in concurrent hash map, like replace or put or whatever. They always do the minimal amount of locking to get the job done, but they never, ever, ever lock the entire data structure. So the entire data structure is never locked. And that means if multiple threads are calling into acquire and release, and you have lots of threads, and they're calling acquire and release in all kinds of interleaved orders, there's no way that you can be sure that other things in the hash map haven't changed while you were busy doing your one thing. And this becomes very important when you write this code. So even though there's no synchronized, explicit synchronizers in this code at all, you're going to have to think carefully about how to ensure that you always successfully end up doing the appropriate update to the map. And there's a couple things that will help guide you here, right? One of which is you have a semaphore, so you can mediate access that way. So remember, what is the purpose of the semaphore in the Palantir Manager? What role is it playing? And this is the case for every single one we've done. What is the semaphore trying to do? Joe? To track the available Palantir. So assuming you've written your semaphore correctly, right? Assuming you have your FareSemaphore, and it works right, that means that there should always be a Palantir available, right? Because otherwise you never would have acquired the semaphore. If you said, let's say the max number of concurrently gazing beings could be 6, right? So the count will be 6. Your semaphore will make sure that there's never 7 things trying to acquire stuff. So there should always be an open, available element in the hash map. However, because of the fact as you iterate through this thing, you don't really know what other threads are doing concurrently, a single left to right pass, using the word left to right sort of loosely, a single pass through every element in the hash map may not actually be sufficient to find the available Palantir. And so you're going to have to think carefully about how to write the code here in order to make sure that you don't do a single linear pass and then through tricks and non-determinism of concurrency end up appearing to find no Palantir even though there is one there. And that's really subtle. The solution is absolutely trivial, but you need to think about it. So I will let you ponder and puzzle out how to do that. Anyway, this code is really, really tight and concise, but it's subtle. Here's release. Release is actually much, much, much simpler because we don't have to worry about any of this kind of stuff. So what we're going to do here is, once again, there should be no synchronizers in this code at all. No synchronized methods, no lock, no unlock, no stamp lock, no nothing. Definitely no synchronized, though. Don't do anything that involves synchronizers. And all you're going to do is, after you do some sanity checking to make sure you're not trying to put a null Palantir back in the map, you're going to put the true value back into the map and release the semaphore. So indicating that there's another thing that's available. And so when you put true, that just means you update that Palantir to be true. It used to be false, now it's true. True meaning it's available. That is a really, really simple piece of code. That's actually going to look very much like what you did before. The difference is, again, there's no need for explicit synchronization because the method that you use to update the map will have the synchronization built into it. So you don't have to worry about it. But again, always keep in mind that any operation on a concurrent hash map does the minimal amount of synchronization to do its thing, and it never locks the entire map. Okay, so that's the overview of Concurrent Map FareSemaphore Manager. The hardest method there is acquire, and that's short, but you'll have to think about how it works. Let's now go take a look at the FareSemaphore skeleton. And this is the one that the undergrads have to do. This, as you'll see, will use the specific notification pattern. So here's some of the stuff you'll have to do. You'll have to define the field that's used to keep track of the number of available permits. Now that you've done assignment 3B, that should be real easy because it's the same thing. but make sure you do it the same way, correctly. Then we have this waiter class. As you'll see, this is kind of an interesting class. It just has a single field called mReleased. That's all. And you'll see that this is what is going to be used to keep track of the waiting threads. We also have a wait queue, and I recommend implementing this as a linked list. You could do it as an array list as well, but linked list probably works pretty well. And notice it's just going to be a good old naked linked list, no synchronized linked list or concurrent linked list or concurrent queue or anything. It's just a linked list. And we're going to rely on the intrinsic lock, the monitor lock of the FareSemaphore MO object to give us any synchronization we need to protect the permit count and the linked list. Your constructor needs to initialize the fields properly to get them set up. Acquire and acquire uninterruptibly. I gave you acquire. So this is what acquire looks like. And we first do a little sanity check here, and then we do this stuff. And acquire uninterruptibly is what you'll have to implement. It looks actually quite a bit like stuff that you've done before, but you have to figure out how to implement it. And make sure that you use a loop and you ignore interrupted exceptions, but you do, of course, keep track of the fact that they occurred, just like you did before. OK, so obviously the devil's going to be in the try to get permit method and the wait for permit method and anything else that they may call. As we'll see in a second, try to get permit is the happy path. This is the fast path where no blocking is necessary. So that, of course, is going to have the right synchronization in it. You're going to have to use a synchronized block here if you're doing the undergrad version. And what it's going to do is it's going to acquire the lock, and it's going to check to see if the queue is empty and if permits are available. And so if the queue is empty and permits are available, then that's the fast path. It will go ahead and return, it'll go ahead and do its thing, and it'll return true, and you're done, right, at that point. So that's the happy path. Now things get interesting. This is the wait for permit method, and this is the one that has all the nitty-gritty details of the specific notification pattern. And so for this, what you'll do is I would recommend you go back and you watch the video that I did earlier on specific notification, and that's where you're going to implement the logic. And this code, again, it's not really long code. It's actually maybe a screen or two full of code, depending on how much you comment it. But it's really subtle. And so that's where you have to figure out how to wait for a permit, which is going to involve making the waiter object and correctly putting it into the queue, into the linked list, and handling exceptions, and all the stuff that we talked about when we talked about how acquire was implemented in the video. So that's where that stuff goes. Release is then the implementation of the discussion in the video about giving back a semaphore into the, or releasing another waiting thread, if there is one, using the specific notification pattern. And remember, there's sort of two cases here. One case is where there are no waiters, which is, again, the fast path. And so you're just going to increment the permit count, and you're done. The other case is there is a waiter, at least one waiter, in which case you're going to take that guy out of the queue, out of the linked list, and you're then going to notify that thread to wake up and run. Remember, as we talked about in the other video, there's an optimization that happens in that case where you're going to essentially not do anything with the count at all if you're going to wake somebody up, because it's a wash, right? You're incrementing, it's going to decrement, just leave it where it is, right? It makes it easier that way. So that's going to be release. And then available permits, this is a no-brainer, but just go ahead and replace 0 with the appropriate field that's keeping track of the permit count. Okay, so all the complexity in this method really is in, or in this class, is really wait for permit and release. That's where you got to really sit down and think carefully about what the heck is going on. But it's super cool. So by the time you get done with this program, you will have a deep understanding of, a much deeper understanding of synchronization and how it works and why it's important to protect shared mutable state in such a fundamental way. Okay, so that's the undergrad version. Here's the graduate version. The graduate version has the same semantics, just is implemented differently, and there's a few extra things we get to do. So we're going to use a condition object here and reentrant lock. So you have to make the field that keeps track of the permit count. No surprise there. The waiter class is a little different. It still has the mReleased flag, but it's got a couple of other fields too. It's got a lock, which is going to be the lock to protect mReleased, and it's also got a condition object, which we'll use to wait notify threads appropriately. So you got to add those things. Pretty easy. Always remember when you're defining fields for things like reentrant lock and condition object, always make sure the fields are the interfaces, like lock and condition. So don't say reentrant lock, don't make the field be a reentrant lock, make the field be a lock that in its constructor is initialized with reentrant lock. Same thing is true for condition. You'll also need a monitor lock since we're not using the built-in monitor locks here, so you'll have to make a reentrant lock to protect the critical section of the FareSemaphore CO. Here's the constructor. You're going to have to initialize the fields in the class. It's a little bit different from the other one, but not much. Once again, we have acquire and acquire uninterruptibly. Those are very much like the ones the undergrads do. This one is a little different. So we're going to have a method here called try to get permit. And if the return value is true, the monitor lock has been unlocked. Otherwise, it's still locked. And this is playing off of the fact that the way that things work with Java conditions objects and reentrant locks is you don't have a strict scope locking idiom there. You can control the way those things get used. So we have try to get permit, that's the fast path. Try to get permit unlocked, which makes some assumptions about the monitor lock being held. And then here's wait for permit and release. And as you can see, once again, that's where all the complexity is going to lurk. The code is very, very similar. The main difference, again, is that because the grad student version doesn't use monitor objects, but uses condition objects and reentrant locks, there's just ever so much more syntax to make sure you acquire the locks and release them in try finally block kinds of things and so on. So the basic, if you took a look at the two things side by side, you'd be able to tell almost one-to-one that they map, that just a bit more syntax here. And there's a few other little optimizations that you have to be aware of as well. And then finally, you have to implement the available permits accessor method to return the count. Any questions about that?